Swayam Prabha. Digital India. Educated India.
Welcome to module 8. In this module, we shall be looking into durability of concrete. So, in the lecture 1, we will talk about some fundamental concepts, look at the degradation process, some definitions actually in the beginning, then some degradation process and some attacks. In this one, we will look into particularly we will look into durability and service life definition and degradation process, in which we will look into actually we will look into first of all we will look into sea water attack, sulphate attack, sea water attack, acid, and we will look at alkali aggregate reaction. So, the 4 things we will look at sulphate attack, sea water attack, acid attack and alkali aggregate reactivity. So, this is the 4 things we will look into in today's lecture 1. In lecture 1, we will look into these ones. So, what is durability? Well, concrete structure may remain stable and safe against load unless deteriorated by environment. Load carrying capacity is one thing. For example, a person may be able to withstand a lot of load, carry a lot of load. So, that is actually stable against load, but same person may be attacked by some virus attack, and may be bedridden, not able to do its function. So, even though strong, able to carry a lot of load, even though it is strong and able to carry a lot of load, may be affected by virus. So, therefore, environment, and this virus comes from where? It comes from environment, it comes from it comes from environment, it comes from environment, it comes from the environment, it comes from the environment. So, load carrying is one thing, but remaining unaffected by virus is something different. Durability related, concrete durability or durability of actually structural systems or materials actually relates to the effect by the environment. That is what we are saying, unless deteriorated by the environment, So, durability is concrete structure may remain stable and safe against load, but it may not still may be safe, but may not be able to do its function, may not be able to perform its function if attacked by deteriorated by the environment, all right. So, that is what we are talking of. So, the concrete structure shall survive and serve its function during the period of intended design life. So, durability is related to this actually, the concrete structure shall survive and serve its function during the period of intended design life. Function means if it is a bridge, should be able to carry the load. If it is a building, should be able to provide the shelter, the structural system in the concrete structural system, it is a part of the building, then it should be able to provide the shelter, support, everything. So, that is the function actually. So, it should be able to carry the function, but then you cannot rule out periodic or occasional maintenance and special repair, because this cannot be ruled out, because the environment may affect. So, when there is it is not able to perform its function, as desired, then you may have to do periodic or occasional maintenance and special repairs. So, define durability. Durability of the structure, component, etc., is its capability to maintain minimum performance level over a specified time when exposed to degradation environment. So, durability of the structure or component, etc., it is capability to maintain a minimum performance level over a specified period of time when exposed to degradation environment. So, if it is in a degradation environment, it should be able to perform its function for a specified time, and that is what is durability, related to durability, right. So, durability is defined in this manner, right, and performance are the measures of fulfillment of functions, that is what by definitions. Performance varies with time, and degradation is defined as a gradual decrease of performance with time. So, these two are related. Degradation is gradual decrease of performance, and if you are able to maintain the performance, that is related to durability, right. So, it is capability to maintain this performance in the environment, its capability to maintain this environment, right, but degradation would it will cause actually performance, it will cause decrease in performance. So, therefore, it is kind of a qualitative statement that we maintain, that is a qualitative statement that we all these are qualitative statements. It should be able to maintain its performance. How do we define this performance? But we said for a given life, given time. So, it is given time, we defined it as a given time. So, for a period, specified time when exposed to degradation environment. Therefore, it is linked to life or time. Now, we can understand concrete will not be maintenance free, it will degrade. Why it will degrade? Because all those material or system that is produced at the expense of energy, by spending energy, they will have a tendency to dissipate that energy. For example, lifting a body up to this level, I increase its potential to mgh. So, it will have a tendency to come down. So, if you give some energy, mgh increases potential, it will try to come down. Now, this is of course mechanical, this is a gravity potential I have increased, but when I am producing a material with the expense of energy, actually energy is input to it, I am increasing its chemical energy or chemical potential, or gives free energy and so on and so forth. So, its chemical potential actually I am increasing. So, when I increase the chemical potential, it will have a tendency to react and dissipate that energy, get involved in an exothermic reaction and dissipate that energy. Now, cement is produced with considerable amount of energy, and therefore, cement reacts with water and dissipates some of this energy, but all the energy is not dissipated, it is not 100% stable material. Had it been stable material, CHS would not have reacted with anything else, and CHS would have been available in nature. The material those you get in the nature, let us say quartz sand, it is available in nature, it has dissipated all its energy and come to a stable state, crystalline stable state, molecules at its perfect minimum potential level. So, whatever materials, whichever material you produce with the expense of energy, has a tendency to dissipate this, and therefore, cement concrete is no exception. Cement concrete is no exception, and therefore, it will not be maintenance free. So, it will have a tendency to react. Concrete will, some component of concrete, particularly cement system, cement hydrate system, that has not dissipated its energy fully, and therefore, it will have a tendency to react. Aggregates actually, if it is fine powder, then like after abrasion, natural process, fine sand, very fine sand, large sizes also has got reduced. So, all the fracture, it has dissipated by fracture all energy possible and come to the finest size. That is actually a stable material. Rocks may not be all the time stable, compared to, of course, fine powder of the same material, because it will have, it can still break into new surfaces and dissipate some more energy and create new surface, dissipate some fracture energy and create new surfaces. So, aggregates, some of the aggregates, some energy might be locked in aggregates, but not necessarily. It is mainly the cement paste and cement hydrate system that has a tendency to, it has a somewhat higher chemical potential, and we would actually tend to dissipate that given an conducive condition. So, cement paste, steel also, and many other material, all materials that we produce with the expense of energy will have a tendency to dissipate. So, therefore, cement concrete is no exception, and it also degrades with time. It will react and degrades with time. All reaction may not be dangerous, but if the reaction is causing, is creating a problem as far as its functional performance is concerned, it is not able to maintain its functional performance, then we will call it degradation. So, functional performance should be reduced. So, you see the degradation, if I kind of plot it along this direction, to start with it is 0 here, and then with time it degradation increases, and this somewhere we define a limit up to which I cannot, beyond which I cannot accept, the degradation anymore. That limit is, I call as serviceability limit, because it will not, we are talking of elements, not the structure as a whole. Structure as a whole will never deteriorate altogether, very rare cases it would. Mostly part of the structure or one of the elements will actually degrade. Degradation you will see in elements, concrete will degrade in some of the elements only, and when it degrades with the element might reach its serviceability limit. For example, I might define those serviceability limit, which I cannot tolerate, say deflection, large deflection, usually the cracks or spalling. So, when it cracks has appeared at certain level, I may say that, well, it is no more acceptable to me, this size of the cracks, and that is my serviceability limit. So, degradation causes those cracks to appear, and when it reaches this, I call this as a service life. And service life, when I am talking of elements, not of the whole building. So, it is of the elements, of the element, concrete element. Degradation normally do not cause failure of the structure unless you have allowed it to go through. So, a component might show degradation and cracking might result. Now, one element, a beam in a large building exhibits crack, it does not mean building is going to immediately fall down. So, all you can do is you can repair it essentially and do some maintenance work, and it will come back to its original, you can bring it back to its original state. So, this may not, most of the degradation do not lead to immediate failure, and when you are talking of life, service life, we are talking with respect to element. I am talking in the context of concrete. You can imagine even in a steel bridge, truss bridge, an element shows some cracking because of fatigue, maybe over the years reversal of stresses, it shows a fatigue fracture. So, you remove that element, put in another one back, the bridge is still okay, it can last for longer period of time. So, such kind of long term durability, or one element shows some kind of rusting. So, you remove that element and then put in another one. So, this you can repair it basically, but in the meantime you have to see that it remains stable, because one critical element if you remove, it may cause secondary effects. So, that is other issues, but all I am trying to say is with respect to concrete, when we talk of service life, we are not talking of the whole structure, you are talking of only an element where visible crack or something is there appear. Now, this is the way we can actually quantify the durability also. So, we set the time up to which it maintains the functions, it is able to perform and able to do its function properly. So, service life is in a way quantification of the durability, all right. Service life is in a way quantification of the durability, all right. So, this is related to the durability. Now, maintenance policy, if I look at it, this, as I said, with time the degradation will progress, Initially there may not be any degradation, and then degradation may start, and this is my serviceability limit, and this is largely related to maintenance policies and repair of structures. Degradations are largely related to maintenance policy and repair of structures, concrete structures, but the cost involved could be very, very large. So, because there are other costs such as disruption cost, you stop a bridge, there is a cost involved in that. Therefore, we would not like, we would like a maintenance free service life, maintenance free intended design life. Intended design life is that life for which I have designed the structure. I have taken the load, the worst load that can come during the intended design life, and the structure should last during that period, and I prefer that there is no repair or maintenance during that period of time, because otherwise it will involve cost. But supposing it happens also, then this is what the deterioration or degradation will, it reaches this limit, and I might do a normally this is the acceptable limit, but I might do at this stage itself I might do some repair and bring it back and go on doing this repair again and again. This could be one of the strategies, but a better strategy, and this is the intended design life of the structure itself, intended design life of the structure itself. So, I can have several service life of element within the intended design life, and I can go on repairing with the original system itself, but I can do a better maintenance or better repair such that it reaches straightaway the intended design life. So, there can be different maintenance policies, and durability of concrete is related to these issues. Actually, durability of concrete is related to these issues, all right. So, maintenance policies are related to this. So, degradation processes in concrete, we now digress or rather go into the material with discussion that we have related to durability, right. Due to the degradation, deterioration occurs. Deterioration occurs of the structure or the element occurs because of degradation. So, it degrades, degradation is going from functional performance reduces, and therefore, the structure deteriorates. So, deterioration, degradation, this confusion should not be there. Now, we are talking of degradation processes by which actually concrete element will get deteriorated. So, sulphate attack is one of them, sea water attack is other, acid attack is other. Concrete is an alkaline material, or cement paste, cement hydrate is an alkaline material, because calcium hydroxide is produced, calcium silicate hydrates are produced. So, they are generally alkaline in nature, relatively alkaline in nature, and therefore, they do not get attacked by everything. It is relatively stable compared to many other, let us say, man-made material, which can so all man-made material do not get attacked by the same mechanism, by the same agents. So, sulphate can attack cement based materials or concrete, sea water can attack the cement based material and concrete, and acid can attack the cement based materials, because it is alkaline. These two, carbonation and chloride ingress, they are not degradation process for concrete per se, but they are problem for reinforced concrete and pre-stressed concrete, because they can cause rebar reinforcement, steel reinforcement corrosion. So, carbonation and chloride ingress leads to rebar corrosion. Other one is alkali aggregate reaction. This is another kind of deterioration, involves aggregate themselves. This involves cement paste, and frost action involves everything, of course, not the reinforcement. So, we look into first this one and then look into this, sometime later on we can look into this one after of course, this discussion, because this is very, very important. Good lot of structures all over the world are affected by this one, and maximum cost for repair is involved with this particular one. But one thing important, there are many deterioration process, but all involves actually chemical reaction, and this is most often presence of moisture is is absolutely must for most of this reaction to occur. Very rarely dry concrete get affected by anything. So, therefore, it is very important that we keep this out. If you keep this out of the concrete system, then it will not, its durability will be infinite, right. And many cases, of course, ingress of aggressive chemicals from outside takes place. So, some cases you can model them to diffusion processes, because if the process is of diffusion coming in, diffusion will define this somewhat sometime later on. So, if the some process can be actually modeled through diffusion. So, but what we got to understand, this is most important, moisture is most important. If we can keep moisture out, all problems are solved. And in some other cases, other aggressive chemicals from outside, it is mostly aggressive chemicals from outside that come and attack the concrete and causes degradation of the material. So, let us look at first the sulphate attack. Sulphates reacts with calcium hydroxide and tricalcium aluminate and forms two compounds, form compounds like ettringite and gypsum. This we have seen earlier, formation of ettringite we have seen earlier when we talked of setting of concrete. Remember, we add a little bit of gypsum, calcium sulphate we add to the cement in order to control the setting process of cement, and C3 has a high affinity for sulphate or gypsum. So, if you have some sulphate, other kind of sulphate, say sodium sulphate is available in the groundwater and your concrete is in contact with the groundwater, or similar other situations where it is in contact with sodium sulphate, it will react with sodium sulphate or potassium sulphate or similar sulphate. Alkali sulphates are most soluble. So, there will again it has to work, it works, it reacts in the solution phase. So, therefore, they are readily soluble and they can react with calcium hydroxide forming calcium sulphate and sodium hydroxide, forming calcium sulphate and sodium hydroxide. Right. Now, calcium sulphate is ettringite, calcium sulphate is something in the gypsum, you remember it was calcium sulphate, 2H2O is the gypsum. So, calcium sulphate can easily react with calcium aluminate hydrate. This is way of writing calcium sulphate. If you remember, when we talked of cement chemistry, we said S bar stands for SO3. So, C stands for CaO, therefore, Cs bar stands for calcium sulphate. So, calcium sulphate reacts with tricalcium aluminate hydrate, forming a complex salt of alumino sulphate, calcium alumino sulphate with so much of water and calcium hydroxide, and these are ettringite. This is ettringite. Now, this ettringite when formed during the hydration process or initial setting process, there is no problem, because the volume expansion, this material, it occupies more volume than the reactants. These are the reactants, this is the reactants, and this is the volume of the other reactant. So, volume of this one, V of this one is less than the V of the product. V of reactant is less than the volume of the product. So, therefore, there will be a kind of, it will try to expand, but this expansion is not a problem when it is actually volume of product is greater than volume of reactant. So, it is not a problem when it is occurring in plastic paste, because this can accommodate this expansion, this can accommodate this expansion, and this ettringite is of course converted into monosulfate and so on so forth, which is stable, but this can expand. But here this expansion in hardened concrete cannot be it cannot withstand it. So, if you have hardened concrete and if something is trying to expand from inside, something is trying to expand from inside, something is trying to expand, it will push, actually it will push the hardened concrete, push it, and normally popping out from the surface will result. So, therefore, disruption of the concrete will occur because of sulphate attack, So, disruption popping out could be occurring. So, this is what happens when you have any other sulphate other than magnesium sulphate coming into the system. Instead of sodium sulphate comes, potassium sulphate comes, they react with calcium hydroxide forming calcium sulphate and sodium hydroxide or potassium hydroxide. Now, potassium hydroxide, sodium hydroxide do not create much of a problem to the concrete, because they are anyway there in the system as well, alkalis are there. But magnesium sulphate, when it comes, it of course reacts with the calcium hydroxide when it is contact with the concrete, but it forms calcium sulphate, but forms also magnesium hydroxide. Magnesium hydroxide of course can react, can form magnesium sulphate, but that is not the case usually. This calcium sulphate of course will lead to formation of ettringite, but problem is CHS is unstable in the presence of magnesium hydroxide. Calcium silicate hydrate is unstable in an environment of magnesium hydroxide, it is quite stable in a calcium hydroxide environment, but in a magnesium hydroxide environment it tends to form this magnesium silicate hydrate. And this magnesium silicate hydrate does not have the cementing property. This does not have the cementing property as our ordinary cement, it does not have cementing property like our binding property, does not have binding property like our ordinary for our cementing or calcium silicate hydrates, and this can result in further decomposition of the concrete. This can result in further decomposition of the concrete. So, what you see? Normally you will see white crystals of gypsum cracking and spalling. So, one thing important from this discussion so far is that magnesium sulphate is more dangerous than sodium sulphate, potassium sulphate. If calcium sulphate comes in contact with the concrete, well, there is no need for formation of calcium hydroxide to calcium sulphate, it will straight away react with the tricalcium aluminate hydrate. So, you see actually white crystals of gypsum cracking and spalling in all cases in case of sulphate attack. All right. So, that is sulphate attack. There are a lot of people there is some lot of research goes on sulphate attack. It's generally comes from the groundwater contaminated with sulphate, foundations could be affected by them by the sulphate attack. White powder of gypsum together with powder formation of scratching are symptoms of sulphate attack. So, you will see white powder, and if you scratch the concrete, you just scratch the concrete, if this is your concrete surface and you scratch it, you will find that materials are coming out. So, on scratching, material will just simply lost from the surface, because the expansion has actually weakened the concrete straight away, and sometime later on it itself will come out. So, that is the symptom of sulphate attack. Now, how do you reduce it down? If you are if you foresee the sulphate attack, then lower water cement ratio is a good solution. It improves the sulphate resistance and is primary protection measure. So, basically you have to reduce down the water cement ratio. What it is, the sulphate will not be able to penetrate into the concrete. Sulphate will not be able to penetrate into the concrete. As we said, moisture has to come in, the other material has to come into the concrete. So, sulphate will not be able to penetrate into the concrete, and that is how it saves. Low C3S cement, sulphate resisting cement. Remember, we talked about sulphate resisting cement when we were talking of type of cement. This has got C3A content restricted, low C3A content. blended cement, of course, cement with pozzolana also improves sulphate resistance. Why? Because first of all, what it would do is it would reduce down the it would reduce down the C3A active C3A content, because cement will be 70%, let us say 30% is my fly ash. So, obviously, C3A gets reduced by 30% itself. If it was 8%, it will now become 5.6%. If I am using about 50% slag in the blended cement, that is your blast furnace Portland slag cement. So, you will have now 8% C3 was there originally, now it will become 4% C3. So, there is a dilution effect straight away, and that improves the sulphate resistance. Beside, normally pozzolanic or blended cement has got better microstructure, they solidify the whole thing, and therefore, they improve the sulphate resistance. So, this sulphate attack, and beyond that, of course. So, using sulphate resisting cement, blended cement, low water cement ratio, these are usually the strategies against sulphate attack, provided you can see them. It's there, but in Indian scenario less common than, let us say, reinforcement corrosion. Reinforcement corrosion is one of the major problems. Seawater attack. Well, seawater contains sulphate, and it also contains chloride, sodium chloride. So, seawater contains sulphates are there, magnesium sulphate, calcium sulphate, they are there, and one difference is that ettringite and gypsums are soluble in chloride solution. So, if you have sodium chloride solution, which is the seawater, the ettringite that would form within the concrete and gypsum, those will form within the concrete, they will get dissolved. So, therefore, there is no scope of actually expansion and cracking. So, the action is slightly different, although you have same sulphate, but the action is different, because now the sodium the chloride solution will dissolve this ettringite, but results in what? Leaching. So, therefore, severe leaching could be there if sulphate attack is prominent. Dissolution of gypsum and ettringite would result in actually very porous concrete. So, if you have very porous concrete, now more water, more seawater can go in. So, crystallization of salt in the pores can occur, and this can cause expansion and cracking. So, some salt pores will become porous, it will become porous, the skeleton will become porous, and therefore, more material can go in, solidify there, and as the crystallization of solid occurs within, this can cause expansion and cracking. But major problem comes from the reinforcement corrosion, because the chloride that goes in, that can initiate corrosion. We will discuss about that sometime later on, but it is the chloride which is more dangerous, because this can initiate river corrosion. So, in the seawater environment, river corrosion is more important. Therefore, one sulphate attack directly may not affect it, may not cause cracking, but it makes it porous, the skeleton becomes porous, and therefore, more chloride can get in and it can initiate the corrosion faster. So, indirectly it will actually helps the reinforcement corrosion. Blended cement performs best in seawater, lower water cement ratio and quality of concrete, of course, is the other method of protection. Now, why blended cement? You see, remember, in seawater you need protection against both chloride as well as sulphate. Now, it has been observed that the penetration of chloride, or the ingress of chloride is not restricted by sulphate resisting cement. Sulphate resisting cement does not perform very well in a chloride environment, because chloride can still penetrate in. In fact, chloride, we will see that chloride binding becomes lower if it is sulphate resistance, because C3A helps in chloride binding, or tricalcium aluminate hydrates, they help in chloride binding the chloride chemically, and sulphate resisting cement. So, if you reduce down the C3A, action of chloride may become more pronounced, while in blast furnace slag cement this effect is not seen. So, it performs very well both against chloride as well as sulphate. So, in seawater, a blast furnace slag cement would perform much better. Then of course, the sulphate resisting cement, sulphate resisting cement, sulphate resisting cement. So, sea water attract it is different. Now, magnesium sulphate also can be present in sea water, and they as we told, it attacks the skeleton of the concrete itself. It attacks the skeleton of the concrete itself. So, in sea water situation, magnesium sulphate can be more dangerous. They can attack the CHS, and there where more CHS is there, basic structure can still be attacked by magnesium sulphate. Magnesium sulphate. So, that's more dangerous. One has to really look into. Now, a lot of research are going on, because with the advent of high strength concretes, we are trying to form more CHS in the skeleton, replacing calcium hydroxide as much as possible. And calcium hydroxide of course, is vulnerable. You have sodium sulphate, because it will form calcium sulphate. But CHS more means less calcium hydroxides. So, it is good if the concrete is exposed to sodium sulphate or calcium sulphate, but magnesium sulphate high CHS may not be a solution. So, a lot of research are going on, and it requires possibly more research to look into this issue. So, next we can look into acid attack. Concrete is alkaline, Portland cement environment is alkaline, therefore, it will be attacked by acid. So, acid comes from where? Sulfur dioxide, carbon dioxide and such other fumes, if in presence of moisture, for example, you have H2O plus SO2 will form actually H2SO3. Sulfuric acid, which might get oxidized to which might form actually H2SO4, H2SO4 in presence of water, etc., etc. So, it might form H2SO4, which is stable actually. Similarly, carbon dioxide plus water forms H2CO3 by carbonic acid, weak carbonic acid. Now, these acids can react with calcium hydroxide. So, this can react with calcium hydroxide, this can react with calcium hydroxide. So, acids can react with calcium hydroxide, acids can react with calcium hydroxide, right. Acid can react with calcium hydroxide, and this can result in acid can react with calcium hydroxide, and this can result in acid can result in it can result in a reaction of acid can result in actually degradation of the concrete, because calcium hydroxide reacting with the acid, would form salt, and this can result in formation of products which would result in degradation. So, acid can attack concrete, acid can attack concrete, acid can attack concrete, acid can attack concrete, right. Now, pH below 6.5 attack initiates, and it is severe if pH is 4.5. So, concentration of the acid matters. Sulfuric acid, the formation of sulfurous acid or similar one, or CO2 carbonic acid, if concrete comes in contact with pH less than 6.5, attacks initiate and is very severe in 4.5. So, it actually caused a lot of loss of the material from the concrete itself. Another acid attack would be because of H2O reacting with H2S, which can actually form sulfuric acid, which can again form actually sulfuric acid. So, this is seen in H2O dissolved in moisture films in sewers is oxidized to sulfuric acid. So, H2S, H2O plus oxygen in the atmosphere, it is dissolved film, it can actually result in formation of sulfuric acid. So, sulfuric acid this can result in again a reaction of the similar kind as we have discussed. Now, attack by dissolving and removal of part of the cement hydrates normally leaves weak mass. So, that is what it is. It actually causes kind of leaching. So, it will attack calcium hydroxide, and in calcium hydroxide, and it will be removed, and if it is, this mass becomes weak, and in in this lower alkaline environment, CHS itself may not be as stable as it was otherwise, and it is not actually, it is porous also at the same time, because calcium hydroxide has been removed by by formation of salts. Normally, acid leaves a kind of weak mass, and this weak mass gradually tend to pop out, Reduction of calcium hydroxide by treatment with sodium silicate helps in formation of calcium silicate and reduction of calcium hydroxide, because this link is calcium hydroxide, the link is calcium hydroxide. This is what reacts with any kind of acid, acids. Therefore, if I remove, if I know that there is a possibility of acid attack, I can actually reduce down this calcium hydroxide by treatment with sodium silicate, and calcium silicate would be there, and this is reduced on the calcium hydroxide and potential acid attack. It can reduce on the potential acid attack, potential acid attack can be reduced. All right. So, surface treatment and coating also reduces the risk of such attack. Even water, pure water, 7 pH water, distilled water, they have a tendency to actually leach out, cause leaching from the concrete. So, concrete close to neutral or less than neutral, that is acidic water, has a tendency to actually become more porous, and in the process they can form weak mass. In fact, you might see white crystals of calcium sulphate in the sewer line between the maximum water and the minimum water line, and weak mass of concrete in the gradually gives rise to popping out of the surface concrete or surface concrete loss. So, coating etc., they reduces the risk of such attack, and blended cement they improve acid resistance, improves the acid resistance, because low permeability, nothing can penetrate. So, blending cement gives you a much better microstructure, and therefore, they nothing is able to penetrate. Alkali aggregate reaction, this is another kind of degradation process of concrete, and concrete deteriorates with alkali aggregate reaction. Now, some aggregates exhibit this, not all aggregate will actually exhibit this. Some aggregate which has got active silica, they can react with the alkali present in the cement, resulting in alkali silica reaction. So, some of the aggregates, not all, some active silica constituent in aggregate when present can react with alkali present in the cement, resulting in alkali silica reaction. The related reactive forms of silica, of course, some of them I have just noted down: opal, chalcedony, tridymite, and there are many others, and they occur in many rocks, opal quartz for example. So, they occur in many other rocks as well. Now, sodium hydroxide and potassium oxide in cement, they form their hydroxyl ion and then reacts with the siliceous materials, forming alkali silicate gel, So, actually sodium oxide can react with some SiO, forming silicate gel. This gel can actually absorb water. This is a gelatinous structure and can absorb water. This gelatinous structures, they can absorb water. So, water can absorb, and then they actually occupy more volume. So, they can absorb water and occupy more volume. So, sodium oxide, potassium oxide in cement form their hydroxides and forming silicate gels, and then silicate gels can occupy more volume. The silicate gels can occupy actually more volume. So, they attract actually water, right, by absorption or by osmosis, and tend to increase the volume. and tend to increase the volume. And this volume, this can, because of the this gel can, the solution concentrations could be different, and thereby by osmosis they can actually attract water. And once they attract the water, they tend to increase in volume, and volume expansion, this volume expansion of this confined gel tends to exert pressure onto the surrounding paste, leading to expansion and cracking and disruption of paste, leading to expansion and cracking and disruption of the paste, right, leading to expansion and disruption of the paste. So, expansion is due to hydraulic pressure generated by osmosis and swelling pressure of reaction product, both, because reaction swelling pressure, or the reaction, swelling pressure will come because gel with water, this product will try to expand, but at the same time there will be hydraulic pressure. The material within, this, if there is a concentration difference, the tendency of the solute would be to move from higher concentration to lower concentration. And if you apply a pressure at the solvent level at the lower concentration end, you will see that this is not actually occurring. In other words, when there is a concentration difference, there is a pressure, there is a kind of pressure that exists. So, if there is a concentration difference, that causes a kind of pressure, and this pressure is nothing but osmotic pressure, and this kind of pressure that would exist within the gel and outside, and also the swelling pressure of the reaction product, that would have a tendency to cause disruption of the concrete, and that is alkali aggregate reaction. That is alkali aggregate reaction, and this is the kind of reaction you can think of. This is one of the reactions shown: calcium hydroxide reacting with silicic acid, forming calcium ion, and this acid plus 2 water, and this is then this two together forming this product and water. So, this product is a gelatinous, has got a gelatinous structure, CaH2SiO4. This has got a gelatinous structure, and this gelatinous structure, it can absorb water and swell and result in formation of the gelatinous material and expansion causing cracking. Typically, they might look like this. This is what we call as map cracking. This is what we will call as map cracking. The structures, you can see the cracks all around the places, So, this is called map cracking. Actually, cracks can appear late from larger aggregate particles. So, if it is from the larger aggregate particle, you may not see the crack in first 5-10 years of its service, and they might come much later, and in extreme case it will simply fall up also. So, some of the other examples of alkali aggregate reaction in the structure is something of this kind, alkali aggregate reaction would be something of this kind, all right. There can be formation of large scale cracks in the system, It will look something like this. This is a real case where the alkali aggregate reaction has caused this particular structure. It's all sorts of splintering out, practically everything is going out, everything is popping out. So, this is an example of alkali aggregate reaction. Some more example. Now, what happens? You have the aggregate, and you can see surrounding the aggregate, you can see this is the original aggregate, and surrounding the aggregate there are white gel formation. This is also similarly, it shows this was the original aggregate, there are white gel formation all around it. So, you can see the gel, surrounding each aggregate. If you look at the aggregate, you will find white kind of gel formation that has occurred. This is a broken piece of the aggregate, concrete, and from this you can find gel formation occurring. And in early stages, you might see fine cracks of this kind, and later stages, this will result in formation of this kind of is a complete crack all around the complete crack all around the places, formation of complete crack all around the places, and structure will disintegrate. Remember, this does not occur, so this is the complete crack in the later stages. Remember, this does not occur in the beginning, it takes at least 5-10 years time. In India, Hirakud dam is an example of, it faced this problem. So, normally aggregates are tested prior to their use, aggregates are tested prior to their use, and then you try to eliminate out the kind of aggregate that can cause the alkali aggregate reaction. So, so far we talked of alkali silica reaction, there is another kind, I will just come to that later on. Prevention of moisture again is the most important, because this reaction also takes place in presence of moisture. This reaction also takes place in presence of moisture. The reaction that we showed, it occurs only in presence of moisture. If there is no moisture, there will be no alkali aggregate reaction. So, even after alkali aggregate reaction has occurred, if one can protect the structure from moisture, alkali aggregate reaction will not continue further. Right in the beginning, if you are able to envisage that there will be alkali aggregate reaction, moisture prevention becomes very important. Use of cement with low alkali content, is low alkali content is important. What you do is actually sodium oxide equivalent to use. Now, sodium oxide, potassium oxide, their molecular weight differs, right. So, molecular weight of potassium oxide and sodium oxides are different. So, therefore, when equivalent sodium oxide content would be multiply the potassium oxide content by a factor, I think it is 0.58 or something close to that. So, such that which is the ratio of molecular weight of the two. So, multiply by this by a factor and find out the sodium equivalent. So, if you use cement having less than 0.6 sodium oxide equivalent or even still lesser than that, then chance of alkali aggregate reaction will be lower. Use of ground granulated blast furnace slag or blended cement or fly ash, they actually reduce the alkali aggregate reactivity. They use the alkali aggregate reactivity. So, blended cement, because 50% the alkali content will get reduced by 50%. Alkalis in the blast furnace slag or fly ash, they do not contribute to alkali aggregate reaction. So, therefore, although they are present, they do not contribute, aggravate the situation. Therefore, using blended cement or fly ash directly or slag directly in the system helps in reducing down the alkali aggregate reaction. Use of Portland fly ash, as I said, pulverized fuel ash, pulverized fuel ash or fly ash in the blended cement with alkali content of Portland cement not more than 3 kg per meter cube of concrete, they do help. And do not use aggregate potentially prone to AAR. Now, how that is done? So, you do what is called, first you do petrographic examination, that is the geological origin of the aggregates are looked into by geological test, looking under microscope and so on and so forth, identifying the mineralogical composition, X-ray diffraction, etc., find out what is the mineralogical composition. And those minerals which are potentially prone to alkali aggregate reaction, you remove them. Normally, say where construction is going on for years together and same aggregate has been used, you will not find this problem occurring, because it is already proven aggregate. But if you are using a new aggregate source, one must do this test. First do those petrographic examination and also do mortar bar test, ASTM mortar bar test, ASTM mortar bar test, mortar bar test to identify whether the aggregate is prone to alkali aggregate reaction. This test, mortar bar test, is done, you make powder out of the concrete, powder out of the fine aggregate, aggregate, make powder, make mortar out of it and then test. All right. So, find out the aggregates which are potentially alkali aggregate reactive and do not use them if it is a new source. So, this is other way of prevention. alkali aggregate expansion reducing admixtures are used. For example, lithium compound. Lithium replaces alkali and products are not expansive. Lithium compounds are alkali aggregate expansion reducing admixtures. So, you use these ones and they can reduce down, but best is to find out that aggregate is not alkali aggregate reaction. But if you still think that you should be playing safer, you can use these admixtures. Also use low cement, low alkali cement actually. Reaction between certain, now alkali carbonate reaction, this is important in some cases. Reaction between certain dolomite, limestone aggregate and alkalis of cement show similar kind of adverse effects, and this is called alkali carbonate reaction. So far we looked at alkali silica reaction or alkali silicate reactions, and this is actually alkali carbonate reactions. Of course, this is relatively less frequent. This is relatively less frequent. So, this phenomena is relatively less frequent. All right. So, with this actually what we have looked into today, we have defined the durability, and then we also defined service life. We have talked about sulphate attack, seawater attack and acid attack, and we also looked into alkali aggregate reaction. All right, we have looked into alkali aggregate reaction, right, and in all cases we have discussed what causes them, and how to actually mitigate. One common point in all kind of attacks in concrete is essentially the presence of moisture. Some cases moisture and oxygen is also required, for example, reinforcement corrosion, but most often it is the moisture. And in all cases we have seen that one thing is we must keep the moisture out, and if we can keep the moisture out, no deterioration of concrete will occur actually. And one more thing, in all cases we have seen low water cement ratio performs the job. So, when finally we actually conclude, or rather we end up summarize our the strategies for better durability and service life of concrete, we will see that low water cement ratio is a requirement, because it is the permeation properties of concrete which is important, because and low water cement ratio actually reduces down the permeability. So, this we conclude this lecture. Thank you.